Next problem. A timber beam is freely supported on support 5 meter apart. It carries an UDL of 12 kN per meter run for the entire span and a point of load is 9 kN at 3.5 meter from the right support. If the stress in the timber is not to exceed 8 Newton per mm square, design a suitable rectangular section with a depth twice the breadth. Design the suitable rectangular section with the depth twice the breadth. These are all the given data. First you see the figure first. So this is the entire simply supported beam. So the span is 6 meter, and from the left support, see 9 kilonewton is acting as a point load. The UDL is 12 kilonewton per meter. So here is the diagram. Next, this one is the shear force diagram. This one is the shear force diagram. So shear force diagram. Positive shear force and negative shear force at distance x, the point is D. So maximum bending moment in the rectangular beam. Given data, the length of the beam L equal to 6 meter, maximum bending stress F max equal to 8 Newton per mm square. We want to find the depth of the beam D in mm and width of the beam B in mm. First of all, we proceed with the let RA and RB the reactions at the supports. RA and RB are reactions at the supports. So here the RA and RB. Here RA and RB. So RA is 41 and RB is 39. So how taking moment about A, RB into 6. RB into 6, that is equal to 12 into 6 into 6 by 2 plus 9 into 2.5. So this is the reactions forces. We got 238.5. So RB equal to 238.5 divided by 6 equal to 39.75. That is in the right reaction, 39.75 kilonewton. But we know RA plus RB equal to 12 into 6 plus 9. So total loads are 12 into 6 plus 9, that is equal to 81 kilonewton. So RA equal to 81 minus RB, that is equal to 81 minus 39.75 equal to 41.25 kilonewton. Next, bending moment maximum at the point where the shear force is equal to 0. Here the case, you see, the bending moment is maximum where the shear force is equal to 0. Here the shear force is equal to 0. So here is the at least right support from X. Here is the maximum bending moment. Shear force is 0 at maximum bending moment. So bending moment maximum at a point where SF equal to 0. Let D the point of distance from right support at which the shear force is 0. SF is 0. SF at D equal to minus 39.75 plus 12 into X, 12X. That is here X equal to 39 divided by 12, we got 3.3125 from the right support. The bending moment will be the maximum at a distance 3.3125 from the right support. Maximum bending moment at D, that is equal to plus maximum bending moment at D, you subtract plus bending moment minus bending moment. Here here is the minus bending moment and as well as plus shear force. Both are just to be. So the bending moment will be maximum at right support. Maximum bending moment at D equal to plus 39.75 into 3.3125 minus of plus 12 into 3.125 into 3.125 divided by 2. So 65.8 kilonewton meter, that is equal to 65 into 10 power 6 Newton meter. Let B and D equal to width and depth of the beam. Here D equal to 2B as given. They are given the data. D considered as 2 times the breadth. So moment of inertia I equal to BD cubed by 12, that is equal to B into D. Substitute D instead of 2B instead of D, 2B cubed divided by 12, that is equal to 0.667 B power 4. Got 0.667 B power 4. Distance of extreme layer from the neutral axis y max equal to D by 2, that is equal to 2B divided by 2, that is equal to B. We know that maximum M by I equal to F max divided by Y max, 65.836 into 10 power 6 divided by 0.667 into B power 4 equal to 8 by B. So just we work out, we got the answer of B cubed equal to 65 divided by 8, 12.388 into 10 power 6. Here B cubed equal to 12 into 12.33 into 38 into 10 power 6. Just we find out B cube root of this one. Cube root of the answer, that is equal to B equal to 231 mm and D equal to 2 times of the B, 462 mm. Finally, we write down the result of the depth of the beam D equal to 462 mm and the width of the beam equal to W equal to 231 mm. Next problem. A beam of T section of flange 150 mm and 50 mm, web thickness 50 mm, overall and depth of the beam is 200 mm and 10 mm long is simply supported with a flange uppermost and carries a central point load of 10 kilonewton. Determine the maximum fiber stress in the beam. You see the beam like this. So 10 meter is the span and 10 kilometers point load, central point load, and AB are the right and left supports. Here the beam cross section is T, like this T channel, T section 150, 50, 50, 150. So there are two sections, 1 and 2. So web thickness 50 mm. Right. Here maximum bending moment of T section of beam. This is the maximum bending moment T section of the beam. Given data, central point load W equal to 10 kilonewton and length of the beam L equal to 10 meter. Okay. Then to find the maximum fiber stress, F max equal to Newton per mm square. So fiber stress in Newton per mm square. That's we want to find. Solution. In case of simply supported beam subjected to a point load, maximum bending moment M equal to WL by 4. In case of simply supported beam subjected to a point load, maximum bending moment occur at WL divided by 4. So 10 into 10 power 3. So W equal to 10 into 10 power 3 into 10 power 3 equal divided by 4 equal to 25 into 10 power 6 Newton mm. Distance of extreme layer from the neutral axis Y max equal to, that is Y bar. See, you see the Y bar equal to A1 into Y1 plus A2 into Y2 divided by A1 A2. So this is the case, Y bar equal to A1 Y1 plus A2 Y2 divided by A1 A2. Here the area of the A1 equal to 50 into 150 and Y1 equal to 75 from the bottom. plus A2 150 into 50 into 175 Y2. So A1 A2. So finally we got 125 mm is the Y bar. Y bar equal to 125 mm. The moment of inertia of the section about an axis passing through the centroid and parallel to the bottom of the face. Moment of inertia of the section about an axis passing through the centroid and parallel to the bottom face. So just we find out the moment of inertia I equal to Ig1 plus A1 H1 square plus Ig2 A2 H2 square. Just to put the values 50 into I equal to BD cubed by I equal to moment of inertia BD cubed divided by 12. So 50 into 150 cubed divided by 12 plus area of the A1 equal to 50 into 150 and H1 equal to 125 minus 75 square plus, so Ig2 also BD cube divided by 12, 150 into 50 cube divided by 12 and 150 into 50, that area equal to 150 into 50 and H2 square equal to 125 minus 175 square. Here the finally we work out and got the answer of 53.125 into 10 power 6 mm power 4. We know that m by I equal to f max by y max, that is equal to f max equal to m by I y max x y max. So put all the values, we got 58.82 for Newton per mm square. So the result is the maximum fiber stress in the T section f max equal to 58.824 mm square.